This is the lesson 4.6 on the fundamental theorem of algebra. So we're going to understand how to use the fundamental theorem of algebra and what that means. And we're also going to be looking at conjugate pairs of complex zeros of polynomial functions. So to get started, these are just two graphs here that we want to identify the number of solutions and the degree. So go ahead, pause the video, take a couple seconds to do that. On number 1, we can see that this crosses the x-axis twice, right? So we're going to have 2 zeros. So the number of solutions is 2, which means the degree, right, is also 2. This is a parabola or a quadratic function, which is x squared, and we know the degree of that is 2. For number 2, we're looking at the number of solutions here. We see 1, 2, 3 zeros, right? And which also means that the degree is 3. The number of solutions is also the degree. So that's a concept that we've been talking about a lot, especially with quadratics. We drilled home that quadratics have 2 answers, and we know that the highest degree, or whatever the degree is the number of solutions. And so we're just going to put a name to that, and that's called the fundamental theorem of algebra. So this is all just saying that if a polynomial of any degree has that number of solutions. So if we take a look at these two examples here, f of x equals x to the 5th minus 4x to the 4th minus 2x cubed minus 1. What is the degree of that function? The degree here is going to be 5, right, because of this x to the 5th value, which also means that the number of solutions is 5. Same concept here. What is the degree? Careful, this one's not written in standard form. The degree is the highest power, which in this case is 3, which is also the number of solutions. Right, so that's what the fundamental theorem of algebra is telling us. If we were given that there are this many solutions, so if we were given that there were 3 solutions, we can also say that we know it's at least the 3rd degree. So how many zeros does this polynomial have? We can see that it's 5th degree, right? It's written here in standard form. So there are 5 zeros. And then we're going to go ahead and find those 5 zeros using our knowledge of factoring and solving polynomials. So our first step here, we need to use the rational root theorem. So we're looking at factors of 8, which are 8 and 1, and 4 and 2, and then factors of our leading coefficient, which are just 1. So our possible roots are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. From there, I'm going to go ahead and use synthetic division. My coefficients are 1, 0, right? We're missing that x to the 4th term. 1, negative 2, negative 12, negative 8. And then again, I'm just going to start with 1. So go ahead and do our synthetic division here. Remember, we're adding these. 2 times 1 gives me 2. 0. Negative 12 times 1 is negative 12. Well, that doesn't give me a remainder of 0 right here. You get a remainder of negative 20. So in order it to be a 0, our remainder needs to be 0. So we're going to go ahead now. I'm going to just try negative 1. I just go down the list. Negative 1. Again, my 1 just goes down. 1 times negative 1 is negative 1. When I add those, now I have negative 1 times negative 1 gives me positive 1. I get, yes, positive 1. 2 times negative 1 gives me negative 2 to get negative 4. Negative 4 times negative 1 is positive 4 to get negative 8 there. Negative 8 times negative 1 gives me positive 8, and I get a remainder of 0. So I know that x equals -1 is a 0, or a factor is x plus 1. Then I'm left with x to the 4th minus x to the 3rd plus 2x squared minus 4x minus 8. Okay, now again, I need to do synthetic division again using the rational root theorem. So my possibilities again are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. And remember, I got that by taking the factors of 8 over the factors of 1. Okay, so again, I'm just going to start with 1. I'm going to start with 1, which we know wasn't a factor already, right? Because we tried that up here and it didn't work. So we can cross off 1 and -1 because those we already know didn't work. So I'm going to move on to 2. And go ahead and try that. So my coefficients are 1, -1, 2, -4, and -8. I'm going to bring down my 1. 1 times 2 is 2. Oh, I'm sorry, that should be +1. 1 times 2 again is 2, gives me 4. 4 times 2 gives me 8. 4 times 2 again gives me 8. I get a remainder of 0. Awesome. So another factor is going to be x equals 2. So I have factors of x plus 1 and x minus 2. Now I'm left with x cubed plus x squared plus 4x plus 4. All right, now I see this has 4 terms, so I'm going to try factor by grouping first. And these, I'm going to group these first 2 and these last 2. All right, in the first 2, I see I can take out an x squared, and I'm left with x plus 1. And in the second one, I see I can take out a 4. And I'm left with, again, x plus 1, which is perfect because then these match, which is exactly what I want. And don't forget our x plus 1 and x minus 2, which then if I simplify this, I have x squared plus 4 and x plus 1. Now, they didn't say just factor, they said find all the zeros. So I'm going to go ahead and set this equal to 0 and then set each term equal to 0. And then from there, we solve for x. And since this is a 5th degree, remember we started with a 5th degree, so we should have 5 zeros when we get done. Here we get x equals -1, x equals 2. This one, we get x squared equals -4. But then when we take that square root, we get x equals plus or minus. Remember, the square root of a negative is I. And then the square root of 4 is 2. So I'm going to just write 2i here. And then we get x equals -1. So this plus or minus gives us 2 answers. We get x equals 2i and x equals -2i. So I have 1, 2, 3, 4, 5 zeros here, which is exactly what we need. Perfect. All right, complex conjugates theorem. That is very similar to our irrational roots theorem. It's just saying that the conjugates are zeros here. So if we have x equals 3 plus 2i, if we're given that that is a 0, then we know that 3 minus 2i is also a 0. So this is going to be a very similar concept to what we already did with irrational roots. So let's just use that same concept to do this. So if you can, go ahead, pause the video, and then complete this writing a polynomial, and then come back and check in. So we know the zeros are x equals 2 and x equals 3 plus I, and that's given right here. Now, since we know 3 plus I is a 0, we also know that 3 minus I is a 0. Okay, so now we're going to go ahead and write those out. If we were to set these equal, and we want to write these as factors, which would be x minus 2. Here we have x minus. This is where it gets tricky again, but again, the same kind of concept as the irrational roots. So we have 3 plus I. And then we also have x minus 3 minus I.